If you like this video, please make sure you subscribe to this channel. So let's look at the problem first. You are given a good sequence, and what is the definition of a good sequence? The definition of a good sequence is that contains letters opening bracket and closing bracket, right? And so if you remove letters and then remove the consecutive bracket pairs, you can make the sequence empty. So let's look at an example. Suppose the sequence looks like this. So if you first remove the letters, the sequence becomes like this. And then if you remove the consecutive bracket, the sequence looks like this. And if you remove this one too, the sequence become an empty. So it's a good sequence. But this is not a good sequence, because if you just first remove the letters, the sequence becomes like this. And then if you remove the consecutive bracket pairs, the sequence looks like this, and there is no pair with this one, right? So this pair gets removed, this pair gets removed, but this will be still remain on that sequence, right? So it's not a good sequence. So suppose a good sequence looks like this. Right? And Takahashi will traverse in that sequence, and he will perform some operations. So the first operation is, if Si is equal to a letter, then he will put that letter into a container, and if Si is equal to an opening bracket, then he will do nothing, and if Si is a closing bracket, then 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 he will find maximum j before I, such that such that from Sj to Si the sequence is good. And after finding that j, uh, after finding that maximum j, he will remove all elements all elements from Sj to Si. He will remove all elements from Sj to Si from the box, from the container, right? So if Si is a letter, he will put that letter into the container, and if Si is a opening bracket, he will do nothing. But if Si is a closing bracket, he will find a maximum j before I, such that from Sj to Si the sequence is good. And after finding that j, he will remove all the elements from Sj to Si from the container. So while doing operation 1, if the letter he wants to put on the container already present in the container, then Takahashi will faint. So your task is to find out whether Takahashi can traverse the the whole sequence without being fainted, right? So this is the problem statement. So let's look at the solution part. So first, look at the third operation first. So in the third operation, whenever you are finding a closing bracket, you have to find the maximum j such that Sj to Si is good, and then you have to remove all the elements from Sj to Si. So I would say that Sj is nothing but the counter opening bracket of Si. So I would argue that Sj is nothing but the counter opening bracket of Si. So what I mean by that is, suppose you have a bracket sequence like that, and suppose this is your I, right? And you have to find the maximum j for which from Sj to Si the sequence becomes good, right? So I am saying that j must be this one, which is the counter opening bracket of the I, right? Because if you choose some other index except j, suppose you choose j as this, or if you choose like j as this one, then what will happen is that this particular closing bracket will not have any opening bracket and opening bracket pair, and that's why uh, it will not be a good sequence, because in a good sequence you have to make the sequence empty by removing consecutive bracket pair. So if you choose this particular j, then this bracket pair will get removed. This bracket pair will get removed, but it will still remain, right? So it will not get removed, and the sequence won't be empty. So you have to choose this j, because by choosing this j, this particular I will get its counter pair, right? So then we can also remove this particular I, right? Then by doing this, we can make the sequence empty. So we can say that Sj is nothing but the counter opening bracket of S. So the second thing is that how to find J for every Si is equal to an open bracket. So we can find this by using stack. So what we will do, that when Si opening bracket, we will append it to the stack. But when Si a closing bracket, then last element of the stack will make pair Si, or we can say that that last element of the stack is actually the j for that particular closing bracket, right? So let's take an example that suppose the sequence looks like this, and this is 1 2 3 4 5 6 7 8, right? So let's take a stack, and first we have found an opening bracket, so we will store the index. Then we have found another opening bracket, then we will store the index. Then there is a closing bracket, and this closing bracket will actually make pair with the last element of the stack, which is 3. So this 3 will be popped out, and our 6 will actually make pair with 3. Then for index 8, the last element of the stack is 1, and this 1 will be popped out, and this 8 will make a pair with this 1. So actually for the 6, for the index number 6, the maximum j actually this one, and for the index number 8, the maximum j actually this one, and we can found that j by using this stack. So after finding the j, you have to remove all the elements from sj to si, right? So suppose this is our sj and this is our si, and you have to remove all the elements from sj to si. And how, and if you want to remove the every element from sj to si, you have to traverse from si to sj, and at worst time complexity there can be n by 2, n by 2 closing brackets, and for each of the closing brackets you have to traverse from that closing bracket into its counterpart opening bracket, right? And this will result in a order of n square time complexity. This will result in a time limit error. So how we can solve this problem? So we can solve the problem in less time complexity by using cumulative sum. So we will take a 2D cumulative sum array, and the row of this array is I, and the column of this array is a particular character. And this 2D cumulative sum will actually represent that up to ith index, how many character element have been seen, right? Suppose for a particular sj and si, up to sj there are 4 a's have been seen, and up to si there are 6 a's have been seen. So we can say that the number of a's present in here is actually 6 minus 4, which is 2. So we have to remove 2 a's from here. So we can just simply find this by using cumulative sum. If we remove that cumulative sum, I of a minus cumulative sum j of a, then we can found the number of a's to be removed, and this can be found in order of 1 complexity, right? So we can find this by using cumulative sum approach. So the dimension of our cumulative sum array will be n by 26, because there are 26 letters that can be possible, and the index can be up to 1 to n, right? So our cumulative sum array will look something like this. So the columns are actually 1, 2, 3, 4 up to 26, and the rows are actually 1, 2 up to n. So for each and every I, we have to found the number of letters seen till now, right? So suppose we are at this index, and for this index the SI is Z. So if SI is Z, that means up to this index, the number of Z that have been seen is actually the number of Z that have been seen from the previous index plus 1, right? So suppose for I minus 1, the number of Z have been seen was 4. Then if at index I we have seen another Z, then the number of Z seen till now is 4 plus 1 is equal to 5. So if we have seen a particular letter, then only the number of that letter will get updated by 1, and rest of the boxes will remain as it was, right? So we can say that for every I, if SI is a letter, then only that particular letter number will be updated by 1. So we can see that cum sum of I comma that particular letter will be whatever the previous value of that letter was, plus 1, and rest of the letters will be remain as it was, right? So here for that particular case, our letter is actually S of I, and for this particular case the letter is actually not is equal to S of I, right? It happens when we see a letter. So this whole thing will happen if we see a letter. If SI is a letter, right? But if SI is not a letter, then there is no new letter seen, right? So from A to Z, or from A to Z, the number of letters for every alphabet will be same as it was I minus 1. So cumulative sum of I comma letter will be as it was in I minus 1. So this will be for every letter. So we can say that if our SI is a letter, then only that particular letter will be updated by 1, and rest of the letters will be remain as it was. But if it's not a letter, then the uh, the uh, the cumulative sum of I comma letter will be same as it was I minus 1 comma letter. So now by doing this, we will find for every I what are the number of each letter we have seen. So if we find I and J, then we can easily find out the number of each letter between Sj and Si in order of one operation. So let's look at the final algorithm. So first convert the letters into numbers, right? Suppose A can be converted into 1, B can be 2, and Z can be 26. So after doing this, build your cumulative sum array, then take a stack, and in this stack you will store the number of opening brackets, right? The indexes of the opening brackets. So indexes of opening brackets, and then take a container which is nothing but an array of size 26. So if you take an array of size 26, what it means by that is its index 0 is actually A, index 1 is actually B, and so on, and our index 26 is actually Z, right? Now what you will do, you will traverse the sequence, and when you find that SI is an opening bracket, then you will append I to stack. But if SI is a letter, then SI is a letter, then you have to update the container, which means that container of letter will be updated by 1 because you have seen a new letter, right? And if your SI is a closing bracket, then you have to find the maximum j, and that maximum j is nothing but stack.pop, right? So this stack.pop will give you the j, and now you have to find out for each and every character how many of those characters lies between si and sj, right? So your removable is actually cumulative sum of, so for each and every character you have to find out this, right? So we will say for k is equal to 1, here 1 means actually a, k less than is equal to 26, that means j k plus plus. So for each and every character you have to find out the removable by doing this cumulative sum of j comma k, right? So these are the removable, and you have to remove those characters from the container, right? Because you have seen a closing bracket, and you have also found the maximum j, and from this range you have to remove all the characters, right? So we will say that container of k, that k means that this particular letter will be container of k minus removable. And by doing this particular operation, if you see that the container already holds that particular letter, that particular letter is already present in the container, you will break and take some boolean, and you will make that boolean is equal to false, and then you will print that no, it's not possible. But if you complete the traversing without breaking, then you will say that this is possible. So there may be some special cases where you have to take a little bit of extra care. Suppose your sequence looks like this, and suppose you are at that particular index where you have found out a closing bracket. So what you will do here is that you will remove all the a's from this range to this range, right? But this particular a has been already removed, right? Because previously you have also encountered this particular closing bracket, and this a has been removed on that previous case, right? But when you have come to this one, you will remove this particular a again, so this a will get removed twice, right? That will result in a negative number of a's, right? So what I mean by that is that, suppose you have found a, so our a is actually 1, then you have found a b, then our b is actually 1, then you have found a closing bracket, and by finding this closing bracket you will remove all the elements from this to this range, right? So this a will get 0 and this b will get 0. Then you have find another a and another b, so our a will be actually 1 and then our b will be actually 1. Then you have found out a closing bracket, right? So you will remove all the elements from this to this range, right? But by doing this, you have removed this particular a twice, right? So this a will become minus 1 and this b will also become minus 1. So there cannot be negative number of a's and b's, which is impossible. So you have to, so you have to take care of this situation also. So what you have to just do, that in on that particular line, before doing, if and that after that particular line, if container of k become less than 0, then make this container of k is equals to 0, right? So that's the extra thing you have to do, and by doing this you will be able to solve this problem. Thank you.